Hi, my name is Midhun and I work with Dr. Jack Burns and the NEST team at CU Boulder, and today I'm going to talk about URSSA, a simulator for lunar surface telerobotics research. URSSA stands for Unity-ROS Simulator for Space Applications, and it's a space environment simulator. Now, why not mission analogs? Because mission analogs are limited in their scope and applicability, and the mission is never the same as the mission analog. Limitations because of difficulty in simulating various physical processes specific to many of these environments. We cannot create analogs for all environments. Financial viability and turnaround times coupled with difficulty to compare with ground truth are some of the issues which mission analogs face. An advent of AR and VR opens new horizons which needs to be tried out. Simulators as enablers for surface telerobotics. Substantial amount of scouting and assembly manipulation activities are there in these new missions, but astronaut time being expensive, some degree of automation has to be incorporated. However, autonomous systems needs to be robustly and repeatedly tested under varying conditions. Similarly, astronaut needs to be trained intensively to respond to multiple contingency scenarios to make sure that they perform consistently and reliably. Hence, simulators are required. How is URSSA an improvement? Our approach leverages on game engines which are fast, scalable and actively developed architectures which can take advantage of high-definition rendering pipelines and physically based shader systems. Environment simulator and the agent sandbox are compartmentalized in our modular plug-and-play architecture. We have been able to get excellent frame rates, and AR/VR compatibility is existing, which makes it future-proof. In our case study, we used a 1 kilometer by 1 kilometer lunar terrain, in which we used the generic rover model, the Spirit rover model. The rigid body dynamics of the rover and the wheel terrain interaction has been handled by the Unity physics engine. We have first person and third person views available. HapKey shader simulates the lunar photometry, which is essentially lack of limb darkening and opposition surge. Wheel tracks have been simulated to basically demonstrate the bidirectional capability of the simulator. Wheel terrain interaction have been modeled using Coulomb friction but can be swapped out for advanced friction models easily. Visual camera, IMU and LiDAR have been modeled, but other sensor modalities can be easily incorporated. The sizes of craters and boulders smaller than the DEM can be easily incorporated by using shape templates and probabilistic generation of shapes and inserting using size frequency distribution. Opposition surge is an artifact of the HapKey shader. What you see here is a wheel proximity based dynamic tessellation which we implemented in this system to have high resolution wheel tracks and at the same time avoid memory hogging by creating locally refined meshes. What you see here is a test case of testing a class of navigation algorithms called SLAM on the URSSA simulator. The top half shows you the Unity environment simulation. The bottom half shows you the ROS simulation. The image stream from the virtual sensors are fed to ROS, where the point cloud is generated using this received data. This shows the possibility of using URSSA as a testbed or for design, research and testing of vision-based algorithms for such extraterrestrial environments difficult to have analogs for on Earth. It can also act as potentially a virtual mission analog. It can also act as sandbox for telerobotics and assembly interface research. The roadmap for URSSA is essentially to have more and more collaborations and to finally release it as open source. Thank you.